Hello my people, I hope we're doing well. This is the second video on 1110, which is Taylor and Maclaurin series. In the first video, we constructed or derived the formula for finding Taylor and Maclaurin series, which is advantageous because in the previous section all we could do was hope that the function that we wanted to find a series for had a relationship to 1 over 1 minus x. Now in this one, we've obviously stumbled upon something far more powerful, and we're able to, for any function where you can find the power series, this will allow you to find the power series. But we did Maclaurin series during the first video because we constructed the Maclaurin series for e to the x, sine x, and cosine x, and then we took a brief excursus to use those power series to prove Euler's formula. Now, what we want to do from here is we want to actually do some Taylor series, meaning we need to find power series for functions that are centered at a place other than 0. And this, of course, is an example right here. We're being asked in this particular problem to find the Taylor series for the given function centered at the given value. Now, we have f of x is equal to cosine x, and a is equal to pi over 2. Now, this is not going to be much more difficult than finding the Maclaurin series, because at pi over 2 you still have those terms that are canceling out, and you're going to wind up with a power series that is, only even or only odd powers. But, and so that's different than the one that we did in class, which we had sine x and it was centered at pi over 4. But let's go ahead and do this one, and then we will move on to further examples. And I think these plus the ones that we did in class will sort of help us get our handle on what's going on here. Now, obviously, if we're going to be using the Taylor series formula, then we need not only the function and the function evaluated at a, because this right here is, of course, f of pi over 2, f of a, right? We need to find successive derivatives and the value of those successive derivatives at our center value as well, our a value. And of course, basically you take the derivative of cosine, you get negative sine, then you take that derivative, get negative cosine, get sine and cosine, and the cycle starts all over again. And of course over here we have the values at which those derivative functions have, the function values at those successive derivatives evaluated at pi over 2. Now, of course, this, and this, we can cross them out because we're not, basically those terms are going to disappear, okay? So the 0 degree term, the 2nd degree term, the 4th degree term, all the even degree terms are going to disappear, and we're going to have only odd degree terms, which is kind of bizarre because remember that the Maclaurin series for cosine was only even degree. Well, that's because at pi over 2, the other ones have 0 outputs. So basically the relationship changes. Now, if we have, and of course this right here is our formula for finding a Taylor series, okay? You have the nth derivative evaluated at a over n factorial times x minus a to the n. Now, if we do that specifically for cosine, we know that we need to evaluate f of pi over 2, and then evaluate f prime of pi over 2, x minus pi over 2 to the first. And the only reason I didn't put a denominator is because it's 1 factorial, right? Now this next one becomes the second derivative over 2 factorial, and then x minus pi over 2 squared. And then the third derivative at pi over 2, sorry, not pi over 4, over 3 factorial, and then x minus pi over 2 cubed, and on and on and on and on and on. Well, like I said, what happens here is f of pi over 2, that goes to 0, that goes to 0, and all that's left is your odd degree terms. Now, f prime of pi over 2, remember, that started off at -1, okay? So what I have here is I have negative x minus pi over 2 to the first plus 1 over 3 factorial x minus pi over 2 to the third minus 1 over 5 factorial x minus pi over 2 to the fifth, and you could keep going, plus 1 over 7 factorial, x minus pi over 2 to the seventh, but we basically get it, right? Basically what happens here is it oscillates back and forth, so I need something that's going to alternate, but we're going to need a negative on the first one, so if our indices start at 0, we're going to need a k plus 1 up here. Now you have in the denominator 1 factorial, 3 factorial, 5 factorial, 7 factorial, and that's going to be 3k plus 1 factorial. And then we're simply going to need x minus pi over 2, and our exponent right here will need to match the factorial, and it'll be 2k plus 1. That right there is the Taylor series for cosine centered at pi over 2. Okay? And, it should come as no surprise that it's also going to have an interval of convergence from negative infinity to infinity and a radius of convergence of infinity itself. Okay, so let's move beyond the trig and the transcendental functions in general, and let's actually look at one that we could do if we wanted to, based upon the old style of deriving it from its relationship to 1 over 1 minus x. So what we're going to do is we're going to find the Taylor series for the reciprocal function centering at 1. Now we can't find the Maclaurin series for it centered at 0 because it doesn't exist at 0. So that's kind of fun. So what we want to do is we want to find the Maclaurin series for this, the Taylor series using the Taylor formula. And then we'll show that is the same thing as we would get if we were to do it by the other method, okay? So, first derivative of x to the negative 1 is negative 1 x to the negative 2, or negative 1 over x cubed. And of course, what you see here is when you take successive derivatives, you're going to start getting factorials in the numerator. This is 1 factorial, this is 2 factorial, this is 3 factorial, this is 4 factorial, okay? And so, but of course they alternate back and forth, negative, positive, negative, positive. When you start plugging in 1, obviously those denominators go to 1, and all that's left is the factorials in the numerator, okay? So what we get here is we get negative 1 to the n, because obviously the first derivative will give you a negative, so in negative 1 to the first being negative, and then it's just times n factorial. All right, so that means that this general formula right here for the particular function that we are given and the Taylor series and the a value that we're given, this becomes negative 1 to the n times n factorial, all of that over n factorial, times x minus 1 to the n. Now remember, this right here comes from the derivative. But notice that that causes both of those factorials to cancel out, and therefore what we have here is we have negative 1 to the n times x minus 1 to the n. Well, those can be combined if you wanted to, and since they're both raised to the same power, that can be 1 minus x to the n. And that actually winds up being the Taylor series. Now, if you wanted to show it out sort of an expanded form, basically it would simply be, it would either be, if you do it from here, you would have to alternate the signs, and so it would be, so plug in 0 and get 1, so it winds up being 1, and then basically plug in 1 and you're going to get minus x minus 1, plug in 2 and you're going to get plus x minus 1 squared, and then plug in 3 and you're going to get negative x minus 1 cubed, and dot, 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 on and on and on. Now, of course, if you did it from here, it would be the same. It would be equivalent. It would just be that those negatives would be wrapped up inside of those odd degree terms. And those are both equivalent, okay? Now, let's relate it back to what we would have done had it been had it been a problem from 11.9, okay? And we remember that everything has to be related to 1 over 1 minus x, okay? Now, that means that if I have f of x as 1 over x, remember, I can change the form of that denominator if I add 1 and subtract 1, right? And then if I do a little bit of magic by grouping, if I put parentheses around these last two terms, that becomes 1 minus x. And so it's of the same form, right? It's of the same form as that one, but instead of x, it's got a 1 minus x, okay? So that gives us, of course, n is equal to 0 to infinity of 1 minus x to the n, or 1 plus 1 minus x plus 1 minus x squared plus 1 minus x cubed. And of course, that was exactly what we got back on the previous page, okay? So the radius of convergence, still the same. The interval changes because it's shifted over, and of course, and the endpoints are still, you still abide by the same rules, since this is actually derived from the formula for infinite geometric series, okay? Now, let's go back to the one that we sort of passed on in class, because I wanted to check something before. I wanted to double check something. What was stalling me is how to deal with those first two terms that are irregular, and before that sort of pattern starts, to use Chris's language. The pattern started in about the third term, okay? So let's actually work back through this again. And it was f of x is equal to root x, and the center being at 1, okay? So, of course, we have the regular, x to the 1/2, and if we evaluate that at 1, we're going to get 1, okay? Now, if we have f prime, we're going to get 1/2 x to the negative 1/2, and f prime of 1. Now, remember, it doesn't matter whether the radical with the x in it is in the numerator, denominator. It doesn't matter what power it's to. If we plug in 1, it's just going to disappear, and the only thing that's going to be determining the output value for each successive derivative is going to be that coefficient, okay? So that's 1/2. You get f double prime of x. You get negative 1/4 x to the negative 3/2, and f double prime of 1 is going to be, guess what? Negative 1/4. You get f triple prime of x, and it's sort of a toss-up as to when you start putting it as a parenthetical number. Sometimes I do it at 3, sometimes I do it at 4. It's just sort of kind of a dealer's choice kind of issue, I think. So negative 5/2, and of course that means that f triple prime of 1 is going to be 3/8. Now the fourth derivative at x is going to be negative 15 over 16, x to the negative 7/2. And that means that the fourth derivative, evaluated at 1, is negative 15 over 16. Now, all of these values should look familiar because these are exactly what we got in class, right? What we didn't get in class is, I stalled because, like I said, I didn't want to give you, it was sort of one of those things I was like, I think it's proper to do this, but I wanted to double check. And actually, I wound up being correct, so that doesn't really matter, but it's just nice to know that my memory hasn't failed me yet. So f of x is equal to, remember that we're dealing with it, n is equal to 0 to infinity of the nth derivative at a over n factorial and then x minus a to the n. All right. Now, if we actually evaluate, if we actually sort of lay those terms out, what we get is, remember, all of these are going to be numerators over the factorial. I mean, I guess you could actually, do it as n is equal to 0 to infinity of x minus a to the n over n factorial times that nth derivative at a, or actually just the other way around. Let's do it the other way around. So let's do that, but let's kind of put the derivative first. So what we really have here is 1 times x minus 1 to the 0 over 0 factorial. And I'm just being, you don't actually need to put all of that, but I'm just trying to sort of show you where everything is coming from. So that becomes 1/2, and then x minus 1 over 1 factorial. And then what we have here is we have negative 1/4 times x minus 1 squared over 2 factorial. And then we have 3/8. And let's go ahead and put those in parentheses just to be really explicit about what we're doing. Okay, 3 factorial plus negative 15 over 16 times x minus 1 to the 4th over 4 factorial plus 105 over 32 times x minus 1 to the 5th over 5 factorial, and on and on and on and on and on, right? Now, obviously, it's really, really easy to figure out this portion of it, right? This portion is pretty simple, okay? That part of the sigma notation is not going to be a problem. What's a problem is how to represent all this. Now, you know that it goes back and forth, okay? But you notice that the pattern doesn't start to emerge until about here. What I was trying to go back and check was whether you can actually write the first 2 terms out explicitly and then add them to a sigma once the pattern emerges. And you can, okay? So what we're going to do is, well, first of all, let's pause for a second and remember that these numerators, 1, 3, 15, 105, that's 1 times 3, 1 times 3 times 5, and 1 times 3 times 5 times 7. And of course, the next one's going to be 1 times 3 times 5 times 7 times 9. And so what we need to do is we need to remember, so let's pause for a second, that anytime you have 1 times 3 times 5 times 7 times ... you're really going 2n plus, to 2n plus 1, right? Because basically the first term, second term is 3, third term is 5, and as long as you're starting at n is equal to 0, or that's the 0 term, that's the 1 term, that's the second term, that's the third term, and notice that they're always, the value of the term, the value of the factor, that is always 1 more than the value for n, or 1 more than twice the value for n. Now remember that actually can wind up, if you have 1 times 3, that's actually the same thing as 1 times 2 times 3 divided by 2, right? And if you have 1 times 3 times 5, that's 1 times 2 times 3 times 4 times 5 over 2 times 4, right? And so what happens here is you have 1 times 3 times 5 times 7, and that's 1 times 2 times 3 times 4 times 5 times 6 times 7, 2 times 4 times 6. Now, that right there is 7 factorial over 2 times 3, or 2 to the 3rd times 3 factorial, right? So you need to basically pull out. So anytime you have 1 times 3 times 5 times 7 times blah, dot, 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 to n plus 1, that needs to be 2n plus 1 factorial over 2 to the n times n factorial. Now, here's the thing. Sometimes sort of doing that works, and sometimes it's not helpful, okay? In this particular case, it helps clean things up, I think, just a little bit. So let's go ahead, having sort of figured that one out, let's go ahead, and that's how we're going to express these numerators. And then, of course, the denominators are simply going to be 2 to the n, okay? And so let's go ahead. Okay. Okay, now what that means is that our first two terms, the ones that don't fit the pattern, is we have 1 plus 1/2 x minus 1, and then we need to have a sigma for n is equal to 2, because this is our n is equal to 0 term, and this is our n is equal to 1 term. And what we need to do is we're going to have to tweak the n expressions a little bit in order to make sure that they fit. But this next term, of course, is going to be negative. So we need this to be -1 to the n minus 1. So that means that the first term generated by this sigma is going to be negative. The second term is going to be positive, third term negative, and so on and so forth. Okay. Now, what needs to happen here is basically instead of having the 2n plus 1, because you start at 2, you're going to have 2n minus 3 factorial over n minus 2 factorial. But that's still going to be, the 2 to the n is going to be 2 to the n minus 2. Okay. So, and then of course that right there is all the numerators. Now the denominators are going to be x minus 1 to the n over n factorial times 2 to the n. And that is incredibly complicated, but still, you know, not terrible. Now, here's the thing. Will it work? Okay, have we figured out something that's going to work? Well, let's go ahead and check. Let's check for the next term. N is equal to 6. Okay, so a sub 6 is going to be, well, it's going to be -1 to the 5th. If I plug in 6 into here, that's going to be 12 minus 9. 12 minus 3, which is 9, so that's 9 factorial. 1 times 2 times 3 times 4 times 5, 6 times 7 times 8 times 9. And then down here, you're going to plug in, this is going to be 4 factorial, but it's also going to be 4 factorial times 4 2's. So it's going to be, instead of 1, it's going to be 2. Instead of 2, it's going to be 4. Instead of 3, it's going to be 6. Instead of 4, it's going to be 8. Now that makes those go bye-bye, and I get the 1 times 3 times 5 times 7 times 9, which is what I wanted to get. And then I get the x minus 1 to the 6th. I get the 6 factorial in the denominator, and I get the 2 to the 6th as well. Okay, and of course that 2 to the 6th was all of those denominators, all of the denominators becoming 2, 4, 8, 16, 32, because every time you brought down the 1/2, 3/2, 5/2, 7/2, 9/2, you were basically multiplying that denominator by 2. And that actually does wind up giving me what I need, okay? That winds up being -1 times 3 times 5 times 7 times 9 over 6 factorial times 2 to the 6 x minus 1 to the 6. And then you can first evaluate that. But that is, according to the pattern, what that next term should be. So hooray for us. Now, the last thing that we want to do might seem a little bit pointless, but fun, is we're going to find the Taylor series for a function that doesn't have an infinite number of derivatives. And you're like, why would you find a Taylor series, which is, you know, an infinite polynomial, for something that already is a polynomial? And the answer is because we can. Okay. So what happens here is if we're doing this correctly, what should happen is I should be able to get a Taylor series. It won't obviously be infinite. It'll be finite. And it should simplify back to the original function. It'll just be in a different form because it'll be centered at -2 rather than being centered at 0, okay? So, now, obviously, f of -2, you plug in -2, you're going to get -2 minus a -8, so that's going to be 6. F prime of x is going to be 1 minus 3x squared. F prime of -2 is going to be 1 minus 12, or -11. f double prime of x is going to be negative 6x, so f double prime of negative 2 is going to be negative 6 times negative 2, or positive 12. And f triple prime of x is going to be negative 6, and therefore it's obviously, it's a constant function. It has an output of negative 6 everywhere. And of course the fourth derivative is going to be 0. So I guess you could actually make it an infinite one. It's just that all of the terms in that Taylor series, starting with the fourth derivative and onward, are going to have a coefficient of 0 because the derivative is 0 after that. Okay. But what that means is x minus x cubed, if you want to rewrite it so that it is centered at negative 2, you take that first derivative, you take that original function value over 0 factorial, and then x minus a negative 2 to the 0. And then, of course, that first derivative at negative 2 over 1 factorial, x plus 2 to the first. And then 12 over 2 factorial, x plus 2 squared. And then plus a negative 6 over 3 factorial, x plus 2 cubed. And like I said, after that, all of the derivatives, so all the numerators of those coefficient expressions, are going to be 0. Okay, well, let's see whether this actually is equivalent to the original. Okay, well, 6, this basically is 1, that's 1, so really this first term just becomes 6. This becomes 11 times x plus 2. This right here, this is 12 divided by 2, so it's 6, right? And that becomes x squared plus 4x plus 4. And then, of course, this right here is 6 over 6, so it's minus x cubed. And of course, if you're going to do it for x plus 2 cubed, you're going to get 3 times 2 times x squared, which is 6x squared. Then you're going to get 3 times 2 squared, 12 times x, and then you're going to get plus 8. Alrighty, let's go ahead and distribute all of these bad boys. And you get 6x squared plus 24x plus 24x minus x cubed minus 6x squared minus 12x minus 8. All right, let's go ahead and gather all of these up. Let's go ahead and get all the constants. So 6 minus 22 plus, that's not supposed to be an x right there, plus 24 minus 8. And then all of the x terms, negative 11x plus 24x minus 12x. And then all the x squared terms, 6x squared minus 6x squared. And then, of course, the x cubed term. By the way, basically negative 22 and positive 24 is a difference of positive 2. 6 and negative 8 is a difference of negative 2. So that winds up being 0. This is negative 23x plus 24, so that's x. This is going to be 0x squared minus x cubed, and oh my gosh, will you look at that. Basically, in doing this, all you've done is you've taken that polynomial and centered it at negative 2. Now, why you would need to do that, who knows, but the fact that you can, and it simplifies back down to the original, I think is pretty cool. But that brings us to an end of this second video as well. I hope that this was helpful in terms of sort of fleshing out further how to find Taylor-Maclaurin series, what the methods are, how the formulas work, and all sorts of fun stuff like that. As always, if you have any questions, please do shoot me an email. Bye.